Welcome to Electricity and Magnetism, Part 8D, Parallel Circuits. And if you remember back a couple sections ago, we said that parallel circuits have two or more loops. These loops are also known as legs or branches. As you can see on the screen, here's an example of a 3-resistor parallel circuit. The current can leave the battery or power supply and flow down any of the legs in the circuit itself. Now, how do we calculate the total resistance of this type of a circuit? Well, we use the following formulas. 1 over the total resistance is equal to 1 over the sum of the individual resistances. Or, to write this out another way, 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over however number of resistors that you have in your circuit. Pretty straightforward. I'm going to do an example, hopefully make it a little more clear. The example is find the total resistance of this parallel circuit. You see it's 3 resistors. R1 is 2 ohms, R2 is 4 ohms, R3 is 10 ohms. And we use the equation right here. 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And the next step is just to substitute in the individual resistances. And in this particular case, I used a calculator and found the reciprocal of each of the resistances. You have them laid out here. Added them up and get this. You need to take the reciprocal of the expression, the equation, excuse me, gives you this, and then doing the calculation gives you 1.2 ohms. Going back to this step right here, some people prefer to leave this part of the operation in fractions and find the common denominator, add everything up, and then take the reciprocal. Whichever way is easiest for you is just fine. Now, adding resistors to a parallel circuit lowers the total resistance. And in a parallel circuit, the voltage is the same in each and every leg. However, in a parallel circuit, the amperage in each leg varies by the resistance. The lower the resistance, the higher the current. Electrons like to flow through the leg with the least amount of resistance. Let's try an example here. Example number 2. Find the amperage in each leg of our example if 0.6 volts are supplied to the circuit. And I've redrawn the circuit on the screen for you in case you've forgotten what it looks like. Let's move that down and proceed to find the amperages. And V equals IR. Ohm's law still holds for each and every leg. And as we said, 0.6 volts are applied to the circuit. That means each resistor receives 0.6 volts. Resistor number 1, V equals IR. 0.6 volts equals current number 1 times 2 ohms. Doing the arithmetic gives us 0.3 amps. Following the same procedure for leg number 2, we find that the current is 0.15 amps. And lastly, we see that for number 3, we get 0.6 amps flowing through that leg. Notice the highest resistor gets the least amount of current. Okay, example number 3. We asked the question, does the amperage applied to the circuit equal the sum of the currents in each leg? We would expect this is true because, as we said before, current is the flow of electrons, and you neither create nor destroy them because they are matter. All right, first number 1, let's find out what the total current in each of the legs is, and that's simply the sum of each leg, and we find out it's 0.5 amps. Now, how much amperage is applied to the circuit? Let's use Ohm's law to calculate that. We see that V equals I times R, Ohm's law. 0.6 volts is equal to I times the total resistance of the circuit, which we calculated above, 1.2 ohms. Doing the arithmetic, we find that it is 0.5 amps, and we see that, yes, indeed, the current in each of the legs is equal to the current supplied to the circuit. I hope that helped. Please feel free to leave a comment.